We're starting our analysis by evaluating the background cloud topology of the unverified satellite video against established public meteorological records. Our primary control dataset is NASA Worldview imagery captured on March 8, 2014. This provides the baseline to investigate the broader disappearance of a Malaysia Airlines Boeing 777. We'll cover how the pattern matching works and evaluate the technical threshold to fabricate these elements. Our geographical focus centers on the southern Indian Ocean. This satellite imagery shows the specific coordinates captured by the Australian government during their search. It's crucial to understand the epistemological limits of this proof. Verifying background data doesn't automatically authenticate anomalous foreground objects. Authenticating the background assets does establish strict operational timelines for any potential forgery. Verifying the background severely limits the time frame a creator had to fabricate the video, but it doesn't inherently validate the anomalous events shown in the foreground. Cloud banks are highly specific, unique spatial geometries. They function precisely like geographic fingerprints. Researchers applied a feature extraction process directly to the unverified footage. They isolated distinct structural nodes within the video background, mapping the specific cloud formations. They projected these extracted nodes onto the established NASA Worldview base layer. Applying an opacity scaling effect reveals exact topological matches, perfectly aligned beneath the wireframes. The statistical probability of naturally occurring duplicate cloud topologies at these exact coordinates and times is effectively zero. The perfect spatial alignment of these atmospheric topologies constitutes a definitive mathematical data match. To align these two distinct satellite imagery sources, researchers had to apply a perspective correction. Standard NASA meteorological data uses a top-down Nadir viewing angle. The unverified video depicts a distinctly different orbital viewing angle. This geometric model shows the required spatial rotation to align the flat Nadir data with the angled orbital perspective. The mathematical transformation stretches the grid points to match the new perspective parameters while preserving the topographical integrity of the clouds. Executing this spatial rotation requires extreme precision to avoid distorting the underlying cloud topology. A precise visual match between these sources is only mathematically possible if the perspective distortion is calculated flawlessly. If we assume a bad actor generated this video from scratch, we have to look at the fabrication threshold. The first immediate hurdle in this process is raw data acquisition. A fabricator would need to access the exact day's telemetry from a secure network before public archiving protocols were even completed. They would then need to convert that flat meteorological data into a realistic three-dimensional environment. Translating flat two-dimensional atmospheric data into a fully realized three-dimensional spatial environment is an immensely computational challenge. There's a massive difference between simple flat image mapping and true volumetric cloud generation. In 2014, rendering true volumetric clouds required an immense amount of computational overhead. To achieve accurate parallax effects within those clouds, a fabricator needed advanced proprietary rendering pipelines. They also faced strict time constraints to process this massive rendering load shortly after the incident occurred. Fabricating this background required direct access to raw satellite telemetry and massive computation, all mapped perfectly to specific coordinates in a matter of days. We return to the baseline of our aligned and verified background frame. If we conceptually remove the aircraft and the anomalous elements, we isolate only the verified data. This logic tree maps the parameters. We have verified checkmarks for time and location on one side, and neutral indicators for unverified objects on the other. The match verifies the background derives from authentic orbital imagery, but it doesn't authenticate the objects inside it. This validation definitively limits the available window for any digital forgery to be completed. The verified background proves the asset is grounded in real geographical data from the day of the incident, but it doesn't definitively prove the foreground event occurred exactly as depicted.